Hi, I'm here to present our work on regret bounds for kernel-based reinforcement learning. Reinforcement learning is a branch of machine learning that can be used to model several learning problems, for instance, controlling robots to reach a goal, playing games, designing recommendation systems, or even self-driving cars. The problem is modeled as an agent interacting with an environment by taking actions and observing rewards, and the goal is to choose the actions in order to maximize the sum of rewards. It's usually a problem that's very hard to solve because it might require a lot of data, and a fundamental question is how to collect data efficiently, which is the context of this work. The environment is modeled as a Markov decision process in which at each time the agent is in a state S, takes an action A, observes a reward according to the reward function R, and makes a transition to the next state S prime according to the transition probabilities P. And the agent follows a policy pi, which is a rule saying which action to take in each state S at each time H. And the goal is to maximize the sum of rewards. So find the policy pi that maximizes the expected sum of rewards obtained by following that policy. If we have a simulator, we can use approximate dynamic programming to find a near optimal policy. And kernel-based reinforcement learning, as proposed in 2002, is an approximate dynamic programming technique that consists in simulating n independent samples from the MDP and using these samples to estimate a model, a transition model and a reward model. And then what is interesting is that you can run dynamic programming on the estimated model with time complexity of order n squared, where n is the number of samples, and we can obtain, as proved in 2002, an asymptotic convergence guarantee to the optimal policy. Our contribution is to design an exploration strategy for kernel-based reinforcement learning to collect data online, so we don't need this assumption of independence between the samples, and we can choose new samples according to the previous ones, so according to what we saw before. And we provide a finite time guarantee on a quantity that can be interpreted as the error per sample, which converges to 0 as the number of samples goes to infinity, and also depends on the covariant dimension of the state action space. And the assumption that we make here is that the model is Lipschitz continuous with respect to a given metric. And here's an example of this algorithm solving a problem. So the goal here is to control this double pendulum so that the bars will reach the top line. And we see that the agent has learned a policy that is able to reach the goal. Well, thank you very much for your attention.